So our next guest speaker is Luca Corbucci. He's a PhD student in computer science at the University of Pisa in Italy. And he's going to be talking us about his latest work called latest completed work. Probably there are other things happening called PUFFLE, Balancing Privacy, Utility, and Fairness in Federated Learning. And really interested about this work. I had the chance to go through the paper very quickly, so I hope to get a complete overview of what it is about. So the floor is yours.
Thank you for the introduction. Can you see my screen now?
Yes, we can see it.
Okay, perfect. So, thank you again for having me today. I will discuss about my latest paper, PUFFLE, Balancing Privacy, Utility, and Fairness in Federated Learning. I'm Luca Corbucci, and I'm a PhD student at the Computer Science Department of the University of Pisa. This is a work that I've done during the period that I spent abroad during the PhD. I visited the Telefonica Research Lab in Barcelona for 1 year, and this was basically the results, a part of the results of that period that I spent there. So I did this work with my co-authors Mikko Aikila, David Solanzo Noguero, Anna Monreale, who is my supervisor on the University of Pisa Sci, and Nicolas Curtellis. And so to start, I will introduce a little bit the problem that we wanted to solve, starting with talking about these three trustworthiness requirements that I mentioned in the title of the paper, that are the privacy, the fairness, and the utility of the model. In the literature, when we started to work on this topic, we found that there are a lot of works that are already trying to solve the problem of training maybe a model that is fair or a model that is private. We couldn't find any paper that mix all these three different requirements. And so we tried to stay in the middle of these three circles, basically. And I want to introduce a little bit these three requirements. One is the fairness. When we talk about fairness in machine learning, we want that a model that we train treats every different groups in the same way, like fairly. So basically, when we predict something, we don't want that this prediction depend on some sensitive attribute that can bias the model in some way. So if I want to make a prediction, I don't want that this prediction depends on some attribute like, I don't know, the gender or the country of that specific sample. And there are a lot of metrics to understand how fair a model is. In particular, we use the demographic parity, but I want to highlight that the entire methodology that I will present can work also with the other fairness matrices. We tested with this one, but it can be used also with others. The only requirement is that these metrics should be differentiable. The second thing I want to introduce is the privacy in machine learning. When we talk about privacy in machine learning, we usually talk about the goal of releasing a model that can be used by users, and these users shouldn't be able to infer any other information about the training data and shouldn't be able to infer new information that they didn't have before starting using the model. The main approach that is used to ensure that a model is private is the use of differential privacy. And in particular, this can be used using the PSGD algorithm that is implemented in some different libraries. In particular, we use one library that is called Opacus. And the last thing, when I talk about utility in this paper, we mean the model accuracy. I think I don't need to introduce federated learning here. Just one thing to simulate. We simulated a federated learning scenario in all the experiment that I will discuss later using Flower, and I will talk more about the experiment and different setting that we consider in the next few minutes. So Before going to our solution, I wanted to highlight a little bit the different limitations of the current solution that we found in the literature. So the first thing that we started like trying to understand what were the solutions that allow us to train models that can be fair. And the first thing that we notice is that most of these solutions are basically only for a centralized learning scenario, mostly because they were originally developed for that scenario, and they are not directly applicable in a federated learning scenario. And this is because of how the data are distributed. For instance, for some of these solutions, you need to compute some fairness metrics during the training of the model. But if a client, for instance, has only samples from one group, you cannot compute this fairness metric because you don't have all the others group and you don't have the metrics from the other groups. And this is a problem that we solve in the solution that we propose. And the other problem that we found is that most of the solutions only tries to ensure either the privacy of the model or the fairness. And mixing these two things is not that common. Was not that common in the literature. There is the third problem that we found is probably the biggest one, because one limitation that we found is that when you train a model and you use one of these metrics, one of these approaches that are available in the literature to reduce the unfairness, the main problem that we found is that you don't know in advance how fair or unfair the model will be at the end of the training. So you just apply the method and hope that it will work. And this, in our opinion, is a limitation. And connected to this problem, there is another one that is that most of these solutions, and especially the solution that propose to do some reweighting, like giving more importance to some samples and with respect to others, they only offer a limited reduction of the unfairness of the models. So, given all these limitations, we started developing PUFFLE. That is our solution. It's an easy-to-use solution that allows to train a federated learning model that can guarantee privacy and a certain level of fairness, while without degrading too much the model utility. Just to give a quick overview of the methodology, I want to start introducing one requirement and one preference that the user of this approach has to set before starting using this approach. So basically, one is a requirement because it's related with the privacy. So before using this method, basically a practitioner who wants to use this method has to set the upper bound on the privacy risk that wants to tolerate. So this is, since we use the differential privacy, we ask the practitioners to set just the epsilon that he wants to guarantee at the end of the training, and instead, and this is a strong guarantee, because at the end we will just say, okay, this is the model that we train, and we guarantee that this is the epsilon for the differential privacy. On the other side, we have the fairness preference. This is a target value for the unfairness that we would like to have in our final model. This is not a strong guarantee like the differential privacy is, but in our experiment, we have seen that basically in all the experiment, our model at the end of the training is really close to this target. Sometimes maybe it's a little bit above, sometimes below, but we are usually close to this target. And this depends a lot on the distribution of the data on which you test the unfairness, basically, because you train on some data, and if the test is really similar, the behavior of the fairness will be similar, otherwise will be a little bit different. Our approach is based on a regularization, because we compute this regularization term during the training, and then we use it to reduce the unfairness. And probably the biggest news the biggest part of this work was the introduction of a tunable approach, because and this is connected to the fairness preference, because based on the fairness preference, the methodology is able to adapt itself to guarantee the privacy and the fairness. And I will talk a little bit about this part in a couple of slides. About the reduction of the unfairness, as I said, the methodology is based on using a regularization term. So we use the regularization, and for each batch, we compute the unfairness of the model, and we use this unfairness as a regularization term. We compute the gradient based with respect to this regularization term and with respect to the classic model loss. And then these two gradients are summed using a weighted sum. And the weight in this case is a parameter that we call that is called lambda. In a previous paper that we cite in our paper, this lambda is a fixed value, while instead we introduce the concept of a tunable lambda that can change during the training. About this tunable lambda, this is probably, I say, the biggest part of the paper, because it's with the tunable lambda we extended the state of the art, the methods that were already available in the literature. Basically, this methodology, the idea of this methodology comes from the idea of having a target unfairness level. So the practitioner, as I said, has to set a target unfairness level, and based on this target, our method PUFFLE is able to compute the corresponding lambda that is able to that is then used to sum the two losses. So when the model is really unfair, the lambda will be higher, basically, and the higher is the lambda, and the more is the important that we give to the reduction of the unfairness. We believe that giving the possibility to just pick a target unfairness level instead of saying you have to decide which lambda you want to use is a method that is easier to interpret, because you don't need to know what's the meaning of the lambda, but you just need to understand what's the metric that you are using to measure the unfairness and what's the level that you want to use in your model, that you want to have in your model. About the experiments, we tested our methodology on 3 different datasets. 2 of them are tabular datasets. One is an image dataset. So for the image dataset, we used the CelebA dataset. So it was a face recognition task. The important part here is that to train a model and to measure the unfairness in this case, we couldn't have just an image, but we also needed some metadata. Like for instance, for each of the images that we consider in the CelebA dataset, we also had some metadata about the content of the image. Like as far as I remember, we used the gender as a sensitive attribute. So for each image, we also knew the gender of the face in the image, and we also had some other metadata that we didn't use. For tabular datasets, it's easier because you already have some sensitive values inside the tabular datasets, and in particular, we use Dutch and a version of ACS income that is like an adult dataset but bigger. And in terms of number of clients, we use 150 clients for the image dataset and for Dutch, while for income, we used a real-life distribution in the sense that this dataset is already split into 51 clients. And because each client basically is a state of the United States of America. And we tested 2 different levels of privacy for each of the datasets, and we tested 5 different fairness targets to see how is the trade-off between the different targets. Like I was saying before, that the more you decrease the target, the more you have to increase the lambda, the more is the importance that you have to give to decreasing the unfairness with respect to increasing the utility of the model. And the last thing, we did two studies. On one side, we studied the global unfairness of the model. So the unfairness of the aggregated model, basically, computed on the server side using some statistics coming from the different clients. And on the other side, we also studied the local unfairness of the different nodes. To compute the unfairness of the aggregated model, the different clients shared some statistics about their predictions, and these statistics are also differentially private to preserve the privacy of the users. So I have some results to show you. I want to start with this one. In this case, we are considering the Celeba dataset. And you can see here that we have 4 different lines in the plot. The black one is a baseline in which we just use simple federated learning training with the Celeba dataset. Red one is the same as the black one, but with differential privacy. And the 2 other lines, the green and the blue, are PUFFLE with fixed lambda in the case of the green line, and tunable lambda in the case of the blue line. In these 2 cases, our fixed and tunable lambda, we use differential privacy and the mitigation of the unfairness. In this case, the target is 0.12, and this is a 6 here, but it's a 8% reduction from the baseline, and at the same time, in terms of disparity, it's a 25% reduction of the disparity, and at the same time, you can see here that compared to the baseline, we have an 8% utility drop. This is the first thing that I wanted to show. The second thing is that, as you can see here, and this result is similar in the other plots, the results that we have got with the tunable lambda is similar to the result that we have got with the fixed lambda. The difference is that, in our opinion, using the tunable lambda is easier because the parameters that you have to set are easier to interpret. So the methodology in the end is easier to use. I have some other results to show you, and I think that it's important to understand a little bit better these results because they are useful to understand the trade-off between the fairness and the accuracy. From left to right, we have 3 different levels of target level for the unfairness. We go from 0.12 to 0.04, and in the middle we have 0.09. These are 25% reduction of the unfairness, 50% reduction of the unfairness with respect to the baseline, and 75% reduction with respect to the baseline. And as you can see, the more we decrease the target, so the more we decrease the target, the more is the utility drop that we have, because without 25% unfairness reduction, we have an 8% utility drop. And then, for instance, with the lowest target, is 0.04, that represents a 75% accuracy unfairness reduction, we have a 17% utility drop in this case. So one important thing to highlight is that it's important to choose a target unfairness value that makes sense to have a model that has both a good utility and also a good fairness. But the thing that our method tries to do is to find a balance between them, because we are able to guarantee a big reduction in terms of unfairness while degrading a little bit the utility, but it's still a utility drop that maybe we can still tolerate considering the big reduction in terms of unfairness. So about some, I have some conclusion and some future work to discuss before the end of the talk. We have presented PUFFLE, and that is a method to train a model that can balance privacy, fairness, and utility by using a regularization approach. We consider it a personalized approach because the practitioner who wants to use this method has to set two requirements. One is a privacy budget, and one is a preference in terms of target model disparity that he wants to achieve. This personalized approach allowed us to introduce the tunable lambda that allows to have an easy to use method. And the experiment showed that for instance, using SELBA, we proved that we can have an unfairness reduction by at least 75%, while also having a decreasing inaccuracy by 75% in the worst case scenario. This is in the worst case scenario that we consider. About the future work, there are still a few things that we are developing now. We are considering a few other problems, and we hope to publish this in the next few weeks. One question that I'm sure someone will have is why you didn't use any other fairness metrics. We are working on this, and specifically, we are working on using the error rate as an alternative fairness metric that we want to introduce in this methodology. And we are also doing some experiments, and we will publish them soon with in a scenario with a distribution shift, because during the training maybe the data could change, and so our method with the tunable lambda can adapt better to this scenario with respect to a method with a fixed lambda. The last thing, there is an assumption that we made in this paper that is the fact that basically the different clients in this paper that we published, the different clients are all unfair toward the same sensitive attribute. The one thing that we didn't consider is that the different clients could be unfair toward different attributes. And so this is another open problem that maybe we will try to solve in the future. So this is the end of my talk. I thank you again for having me today here. And if you want, this is the link to the QR code to the paper, and then there is also a QR code for the code that is published on open source on GitHub.
Great. Thank you, Luca, for the super interesting talk.
Thanks.
I have some questions. Some others in the audience, including you, Jan, have some questions, and feel free to, or if you don't have, think about them if you want. So my first question maybe is an obvious one. Maybe I think could be a question that some reviewers might ask is, if the practitioners have to set up the target unfairness level, how do they know what a good level is? I guess it's a single scalar, but what does it mean? Level 2 or level 8, and does this level change if suddenly I have a bigger pool of clients or a smaller pool of clients, or if I make my model bigger or smaller, those change what the target level should be?
Yeah, we were thinking about a target that depends on specifically on. So this target could depend, for instance, on regulations that are different in the different countries. This was one thing that we thought when we were discussing about this problem. And then it depends a lot on the scenario in which you are. For instance, if you already have a baseline, or you expect a certain value for the unfairness, maybe for the unfairness of the baseline model without any mitigation, maybe you can just say, okay, I want a reduction of X%, and just try to find a solution. If you want the other option is just to try maybe different levels and find a level of unfairness that can be acceptable for you. and can be also good in terms of utility, model accuracy. But the main thing that we were also discussing, I think, in the paper, as far as I remember, was the idea of having a value that depends also on the regulations that you have in the different countries. About the change about a no, not tunable, but about a variable target during the training. We haven't experimented with this problem yet, but it's definitely something interesting to consider. We discussed about this when we were discussing about the idea of having a distribution shift, but we haven't experimented with this thing yet.
Yeah. Could you remind me briefly what is the definition of fairness you are using? I think you
Yeah.
were presenting it at the very beginning.
Yeah, it was in one of the first slides. So the one that we are using now is the demographic parity. And basically here the what this metric wants is regardless of the sensitive attribute. So Z is a sensitive attribute here, and Y is the output of the model. Regardless of this sensitive attribute, the probabilities of having an output should be the same. There are a lot of other fairness metrics, and we are experimenting with the error rate that is similar to this one, but also takes into account the true label of each sample, basically.
Do you think that for this work, would it make sense to, in addition to this, maybe this being the main fairness metrics, also to consider, because the form of fairness I'm more familiar with are those that arise because of system heterogeneity, like some clients have much more data than others.
Mm-hmm.
Should that client with very little data, should it be ignored? Or no, maybe no, because it's a minority, and then if we never include those data points, then it would be unfair. I think this is something that could be captured with what you mentioned at the very beginning, like evaluate the performance, for example, of the global model with the error rate. I think what you meant by that is how the model behaves on each client's validation set or
Yeah,
something like that.
I didn't get what kind of data you were mentioning at the beginning of what you were saying.
I mean, more in general, like how do you see this this method address the fairness, but more that arises because of a system, because of the overall system, like maybe some clients are not always available.
Mm-hmm.
How do you handle that? Or some clients might have a lot more data than others. Should the clients that have very little data be being sampled more frequently, for example, so that knowledge is not forgotten by the global model? I know it's a different perspective to fairness, but
Mm-hmm.
I was just
Yeah,
curious to
it's
see.
so in about the you're right about the amount of data. There could be some problem if you have some clients with a lot of data compared to others maybe they have just a few samples. But we didn't consider too much this aspect in this paper. But it's something that we are more or less working also on this part. About the other thing that you were saying, we were also studying the local clients unfairness, and there are some plots in the paper that I didn't report in the talk, and we were trying to understand the relation more or less between the global aggregated model and the global aggregated unfairness and the client unfairness. But we didn't consider other aspects of the unfairness, like clients that are selected just a few times, because to simplify some things for the privacy, we decided to have a fixed number of client selection for each client. So we didn't consider this aspect.
Yeah, that sounds like a valid answer. I think it's impossible to test everything. So yeah,
Yeah.
cool, perfect. I don't know if there is any more questions. Maybe any questions, Jan or Jan? No. Okay. Well then, thank you very much, Luca. Again, just as I said for John, if anyone has a question, maybe if you're watching this later on YouTube, feel free to reach out to Luca. Probably you can reach out to him by email or maybe even in the Flower Slack.
Yeah, I mean, I'm also in the Flower Slack, so
amazing.